good to go? Yeah. Okay, last, but hopefully not least, and yeah, we've managed to have Murphy's Law kick in here for the last presentation. Yeah, I just want to give you a perspective of my career. So my name is Dr. Zaki Hussein, and I'm the founder and CEO of the company called Touchlab. We're based in Edinburgh, Scotland, and the mission is basically to give machines the power of human touch. So I'm going to give you a little bit of insight into my career journey, and I've put sort of a picture here from the finals of the Avatar XPrize, which was sort of a dream of mine to get to that stage. And I think my story has been quite one of reasonably low probability to get to this point. I'd like to quote Peter Diamandis to start with, who founded the XPrize. So the day before something is a breakthrough, it's a crazy idea. And I'll give you a bit of a motivational video, which hopefully will get you excited. And we had audio a minute ago, so just a sec. It might be muted, unless something has changed. Is it volume up?
Can you try it?
There we go. Yep. Thank you.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Okay. Thanks. So hopefully that got you excited about the talk. This kind of shows a little bit of the aspects of what we work on. So I wanted to start this off also from a quote from Jeff Bezos from the Remars conference in 2019, which he famously tried out the shadow robot system on as well. So I thought it was fitting. He said, if you went back 30 or 40 years and asked roboticists and computer scientists, people working in the field at the time in machine learning, which problem would be harder to solve? Machine vision, natural language understanding, or grasping? I think most people would have predicted that we would solve grasping first. So it turns out that this is in fact the reverse of what happened. And we're still struggling, we're getting closer to solving robotic grasping in a number of scenarios. So my motivation to kind of get into this field is really to try and have some, basically help people and have some impact along the way. But one of the kind of core focuses of the company is actually healthcare robotics. So we've heard a little bit about that already. You all probably know that there's an aging population, and the population is predicted to peak in about 20 to 40 years. That's one of the challenges that we have, and the thesis that I started this company on towards the end of my PhD. So for a couple of years, I was working both on the company and my PhD. But the thesis was basically that the biggest barrier to mass robot adoption in unstructured environments is their inability to feel the world around them. And it's been really interesting because this was in 2018, late 2018. And at that point, a lot of people said, okay, why do robots need touch? I'm sure a lot of people in tactile sensing know this. And in the last few years, we've seen an increasing percentage of the robotics community say, actually, we need tactile sensing. And now it's, I think, over 50% at this ECR this year, which was really exciting. Basically, robots are somewhat clumsy without skin. Skin is the largest organ in the human body. Currently, grippers are pretty dumb, and they don't accurately relay tactile information most of the time. There are a lot of workarounds with different transduction methods, and I would almost call the vision-based method one of these to some extent. But there isn't really a high-performance electronic skin that you can fit around any part of a robot, from the fingertips to the feet, to the rest of the body and could take all the loadings and just repeatedly be used in an industrial setting. So that's really what I wanted to do during my PhD. You can see here an illustration of the mechanoreceptors in human skin, which have, funny names like Ruffini's corpuscule. But basically, they cover a range of different static and dynamic forces, and they enable us to do things like, for example, feel a lentil on our fingertip, but also, go and lift a 50-kilo weight if you're strong enough in the gym, and you haven't damaged the original sensor that was very sensitive. This is a very difficult sensing challenge, one that I thought was pretty interesting to take on. So my research questions when I started my PhD, so this was, just to kind of give you an overview, it wasn't, I had been exposed to entrepreneurship before my PhD. I did my master's in engineering, 4-year degree at the University of York, actually, where TAROS will be next year. My focus had been on electronics with nanotechnology. So I'm from a sensing background originally. And I kind of got into this. I was always interested in robotics, but more in the nanorobotics domain. And that wasn't something that could be, I would say, kind of wouldn't necessarily happen at scale during a time frame that was tractable, in my opinion. And so in order to have impact, I actually tried to apply some of those skills into a different domain, which was a macro-scale robotics in this case. So the research question that I got onto a CDT at the University of Edinburgh for basically was, can a high-density, repeatable, high-dynamic range, tactile electronic skin system be made to solve the real-world grand challenge of dexterous robotic manipulation? And eventually that formed the basis for Touchlab. If we could do this, we could probably do this in many other applications, even outside of robotics, which are quite exciting, even from a medical perspective. So going back briefly, here's sort of a very brief summary of my literature review. I went through all the different transduction methods. Actually, my thesis, which I think is now public, has much more elaborate tables on this. But here's a simple one that I have. And so looking at, piezo-resistive, triboelectric, piezoelectric, all these different methods, and thinking which one could solve this actually at scale for the foreseeable future? Which one's scalable? Which one can do Moore's law in terms of tactile, exponentially increase tactile density and be extremely resilient? So I concluded that, I kind of didn't go for some of these transduction methods because of the amount of noise that they had and were susceptible to, because of integratability challenges and so on. And I'll explain to you which ones I did investigate and how we finally got to the sensing that we currently use. So I started off working in a clean room at the Scottish Microelectronics Centre using photolithography to pattern zinc seed layers onto substrates and grow piezoelectric zinc oxide nanorods on top of them. There's a sort of a scanning electron microscopy image of these, and it was quite interesting. We had to make sure, this was deposited on a silicone membrane, a spin-coated silicone membrane, and so silicone stretches, and in order to make sure that your electrodes made of zinc don't sort of crack completely and get destroyed, you have to make sure that they can flex with the stretching of the silicone substrate. So that was quite an interesting challenge. Unfortunately, this didn't work because the zinc oxide nanorods didn't have a signal that was higher than background noise levels when you actually deployed them in application. So it was not a very good thing. So this was initially based on a colleague's work, and so I tried to elaborate on that, realized that didn't work very well, moved on to a more ductile and malleable material like gold, and realized that you could use the cracks that are being generated in the metal to your advantage. You could engineer the cracks to increase the gauge factor of a strain gauge. So here what you can see is a microscopy image of the wrinkled gold surface on top of a silicone substrate with engineered cracks. And basically it's called a percolating network, and you get these micro and nano cracks, and you get these different These are just for illustration, but you get currents jumping from island to island depending on how much you flex the material, and that changes your resistance. And you can get a very large change in resistance for this. So that was pretty interesting. Made some nice sensors that you see here, and they were very, very thin, and you could put them in gloves and different, directly onto human hands. But they were not resilient. They were not robust enough to be deployed at scale. Again, kind of a dead end, really good for publishing papers, very, very sensitive, but not really what we need to scale this technology up. So by this point, I had started my CDT. I was sort of midway between my PhD. We started a company, actually, based on that technology with a colleague of mine in the research group I was in Edinburgh. And he became the CEO, and I became the CTO while doing my PhD. Unfortunately, I tried to, using physics and science, show that this would not work at scale, that this technology couldn't take thousands of cycles, for example, and the degradation was too severe in the sensor. Unfortunately, those concerns were not listened to at that point. We filed a few patents, we actually got some grants, etc. But ultimately didn't really work very well, and the team ended up imploding because of some misconduct issues. And in the end, I was left, despite being CTO, to liquidate the entire company. It was pretty painful. I almost gave up at this point when it comes to entrepreneurship, because it was quite a painful experience with lawyers and so on involved. But I continued the research, and I had already been looking into nanocomposite material, intrinsically stretchable, intrinsically flexible materials using graphene, carbon nanotubes, and so on. So a different route, no longer clean room based. And here's some of the early results that I got using those materials. Of 8 sensors on my hand, essentially, just to sort of show that the multiplexing is working, etc. Initially, we can test that every sensor is working. So as you can see, got a response from each sensor, the right location. Okay, and now we want to see how to grasp objects. And we can do that with an orange. So it depends on which fingers we're activating. Applying pressure with. Obviously, my grasp is changing. I can, depending on how I grasp the object, it's going to give me different sensors. So I'm not going to go too much into that, but this is basically what was first trademarked as eDermis. It was a 4-wire sensor that could be made into almost as large areas or small areas as you want, and because of the low number of wires, it was quite useful for retrofitting onto robots. This is an example of it being embedded in rubber to be a bit more productizable. And basically, it's a single point resistive sensor, but it has an anisotropic quantum tunneling based ink, and it's a piezoresistive sensor, so it's selective towards normal pressures. You can't do multi-touch with this, but it was sort of something a little bit new from the PhD standpoint. So I started Touchlab. Very reluctantly became the CEO, because now as CEO I have lots of admin duties and had to learn a lot of new skills like accounting, legal, IP negotiation, you name it. So that was interesting. But this was better tech and showed much more promise, and we actually got a first client. I didn't know how to raise money for a startup at this point. So the only way that I knew to start a company, because I had no experience really being the CEO or anything, was to go out to a client and see if I could negotiate a contract, and then they would pay for the R&D. And the great thing is, although part of this became my PhD, the cost of doing all this development was much higher than any of the money I had allocated during my PhD. I had to outsource manufacturing to more precision screen-printed labs and other things. So that was really useful. And then it turned out that having a client from the get-go for a hardware deep tech startup, and just I showed that we could make a profit in year one, it was actually pretty attractive to investors. So I didn't realize that because that was the only way I knew how to do things. It was hard, but yeah. And then kind of going forward, this XPrize competition opened up. I realized there was an XPrize competition in telerobotics. And we'd been doing some vegetable and fruit picking with these sensors, but that was pretty exciting. I'd always wanted to be part of an XPrize, and I thought it would be really exciting if we could maybe enable, presence in a remote location, and that touch could play a key role in there, and it was kind of missing, like good kind of touch. I'll kind of go through this later, but then we basically. I managed to raise some money, build a team with academics at the University of Edinburgh. We tried to get funding from many sources unsuccessfully. Then COVID hit. And then they said, okay, we can't, the university can't keep dedicating these people and resources to you for free. So unless, you pay up, this XPrize project's going to die. And I participated in something called the Scottish Edge competition that year, just in case. We won the top prize, 100,000 non-dilutive pounds, and then investors got interested in putting about 6 to 10 times more than that to help fund this, and hence we had the resources to go towards the XPrize semifinals. So basically going forward, we started to productize a little bit more.
So this is one of our new triaxial sensors. This particular one is embedded in the polymer. It is highly durable and will survive millions of actuations. And if we go ahead and connect it up, plug in our board and connect. You can now see the components of the 3D vector which the sensor gives us, the X, Y, and Z components, where the X and Y are shear forces and the Z is the normal force. The range of these is from 0 to 50 newtons. If we now look at it in a 3D format, we can actually see a graphical representation of that 3D force vector being displayed.
So this
and if we switch to the 2D format.
Yeah, I'll go forward. So this was an example of early productization. We were, okay, can we make a very, very thin sensor that's triaxial? And can we have it easy to retrofit onto existing grippers? Now, this is quite a few years old, but I just wanted to show you that journey of getting closer to product or product market fit. Now we've made a variety of these. We've equipped whole humanoid grippers, and you can see really small triaxial sensors that we have there. I mean, we can actually make them smaller, but this is just an example of the prints and how thin they are. And we've applied them to some interesting use cases, as I mentioned before, picking without damaging. Okay, so I'm going to skip that. We've gone on from there, and we've got some more advanced tactile fingertips now. So here you have an example of a single tactile fingertip with 42 taxels. Each of the taxels with a dynamic range of between around 0.1 newtons to 25 newtons. So you can imagine that if you have a larger pressure across the surface, you can actually lift a lot more than that. And we built over 3 years a custom calibration setup with comparable, so we basically brought the performance to be comparable with the ATI Nano, with the force torque sensors, all in this extremely thin kind of sensor. And this has been a lot of work, frankly, making it really robust, anti-cycling and so on. And what we're trying to do over time now is build on these kind of machine learning layers and interpret, touch features, you could say. So slip detection at scale in industry seems to be something that is still very challenging to do with any tactile sensor out there. There are lots of papers in controlled settings, but making that generalizable is something that we're very interested in. And then, of course, hardness detection of objects and identification of objects through touch, which there have been talks about at this conference. So doing this kind of out in the wild is the challenge we're trying to solve for us and our clients. But then we said, okay, well, why stop there? As I mentioned, we were part of the XPrize, and we worked on a tactile telerobot, which was a bit different to Shadow's. And this was the first one at the University of Edinburgh. This was at Cedric Lamar's lab with his next stage robots. So this was our competition entry into the XPrize. $10 million in Avatar. Stop there. We've got nice music in the background, but so that was our entry. We took that to the semifinals in Miami during the pandemic. While we were having travel bans, the XPrize said, "We're having the competition. Figure out a way to get there. You've all got PhDs. It's not our problem." The robot was easy to ship. That didn't have a travel ban on it, but humans a bit harder to ship. So we had a very horrible experience of spending 2 weeks in the Caribbean quarantining on St. Lucia, drinking rum cocktails while doing the final bits of development. That was our solution. We were really happy. We won $133,000 for getting through to the final stage of the XPrize. Competed against 40 teams globally, became part of the final. It was final 15 or 16 at the time. And then we did 1 year more work and shipped another robot to Los Angeles for the finals. So here's a couple pictures of the new robot being worked on and the skin being added to all of the different parts of its body. Here's our team for the XPrize finals. We merged with the only other UK competing team because Shadow had not yet announced that it would compete at the finals at that point. It was a long story, but Cybercells from Sheffield and us from Edinburgh, we merged into Team Cybercells Touchlab. So that was quite interesting. And here's the joint team. And basically our challenge was to build this teleoperation system and teach a judge within 1 hour to operate it. And so you can see the judge here sitting in a chair, who ended up being the CTO of Figure, actually. So that was pretty good contact. Anyway, so coming towards the end of the presentation, this has kind of been my journey, and it's been a journey of low probability. The financing history of the company I wanted to show you briefly here, because it starts from sort of small grants while I'm doing my PhD in 2019 with my colleagues and some advisors at the technology transfer offices of the University of Edinburgh. They really helped me at the beginning. And then we had to negotiate all these IP situations, and the university had to sign over the IP to the company. And we did it in all a very amicable and mutually beneficial way, but this can be very challenging to do. And then over time, we won the Higgs Edge. Then out of, I don't know how many investors I had to pitch, but probably hundreds. I frankly didn't count, and it was better not to. Most of them said, don't do avatars. It's never going to work. This isn't an industry. Because this is 2018. People were scared of robots still at this point in a lot of Western countries. And eventually some investors bit the bullet, and eventually we even landed Octopus Ventures, which is the Octopus Energy company, and they're now our main backers. One of the biggest deep tech investors in Europe decided, you know what, maybe this tactile weird touch stuff in robotics could make a big difference, right? So we're trying to scale up the technology now. And we launched a robot in Finland last year in a Finnish hospital. Is a sort of a general purpose tele-operated humanoid robot, which basically means it's controlled by a nurse or a clinician in this case. Valkyrie is operated using a haptic teleoperation setup. So you wear virtual reality glasses, you have a virtual reality controller and a haptic glove. You can control all the fingers individually and you can feel touch from the fingertips and the palm. So this is what we did in Finland. We took our XPrize work, adapted it to a hospital, built custom clothing from nurse clothing for the robot and everything, and deployed it in a Finnish hospital for 5 months, taught 14 nurses to teleoperate it, which human factors, I can just tell you, is a challenge. We have sociologists from York who are actually publishing studies on this because they came to study it, so that's quite exciting. But we wanted to do something that hadn't been done before in this space, and ethics approvals were a challenge. You know, making sure the robot was safe was the biggest concern, right? So the amount of safety systems and testing we developed was a lot. And I joke about the fact that now we've got the robotics team that knows the most about nursing and how to do nursing in the country. That was a big challenge. They all went white when we first went into the ward, and we said, yes, we're going to actually try and deploy this. So kind of to wrap all this up, there were many, many challenges to get to this point. We're still going, but my mission, I guess, was to do something that was sort of impactful, to take robotics into the real world. And there were lots of different aspects that were involved. It's a very low probability of success journey, but as already has been mentioned here today, I think if you're intrinsically interested in something, it is worth pursuing. You never know what's going to come out of it. For example, the XPrize. I never thought I'd even be able to form a team. And then somehow, you know, people came and we did. So thank you very much for the talk, for listening.
We have time for a few questions. Is there any? Okay. Yeah.
Thank you so much for your presentation. I'm just still wondering, you mentioned you eventually established how to really calibrate all of this tactile sensing, 40 the tactile sensor calibration, right? So, but that is also my first question is that. And second is that, basically your sensor looks like a very, soft, right? Very flexible. The meaning is that, I'm pretty sure like the hysteresis level is quite really large. Right? So, and then third is that, can you just tell me the quite secret information about your sensor, like the maximum frequency of your sensing?
Yeah.
That's all.
So 3 questions almost wrapped into one of performance and calibration, right? So that's really been the hard thing. I mean, my approach to this was from a materials standpoint because I worked in a nanomaterials lab in Edinburgh. So I think that was maybe beneficial coming to the engineering. You know, I'd worked in a clean room and looked at different fabrication processes. But yes, hysteresis traditionally has been a huge challenge. We've explored using a number of different substrates, including extremely thin silicone TPU composite substrates. In the end, a lot of the substrates we use for if you want the least hysteresis, for example, you would go for a stiffer substrate, but a very, very thin one. So maybe 25 microns thick. Captain, for example, would be an example of such a substrate. It could also be PET. So those ones will not be stretchable, but they will be flexible. And you'll be able to curve them around surfaces of robots. So yeah, very challenging. And having, in our case, we have a material that is partially anisotropic. It means the way it's structured on a micro scale or its formulation effectively means that it doesn't react, it reacts reasonably selectively to the normal forces and doesn't react much to bending. Now, bending does create normal forces inside, so we can get into that one, but we can actually You can either use those in, you can get, well, if you're training neural networks, you might not care of having that additional data, but if you do, it can be calibrated out. So we spent years building a calibration setup. And we have now sort of, it has a robot arm, it has voice coils, it can do extremely fine steps of all of that dynamic range that I mentioned, so that we can show that. I mean, our gold standard reference will be like an ATI Nano 17, so a force torque sensor that's, it's small, but it's not as thin or small as ours, and we then show that we can do, comparable performance. Funnily enough, we don't need to temperature compensate our sensors, whereas the ATI does. So we actually have a huge advantage, just for your information. But it's very challenging. Like, it took many years. My PhD started 10 years ago on this subject, and as you can see, many fabrication process down the line, we're finally finding the thing that really enables that performance. So the maximum frequency, so at the moment, our maximum that we can drive a sensor is 1.5 kilohertz, 1 Tactile. We run the fingertip at normally around 200 hertz at the moment, the one with 42 Tactiles. So if you wanted to do slip detection, for example, you might want to look at higher vibrational frequencies because you're looking at incipient slip, so before the slip occurs. And at that point, you might want to poll taxal regions or local taxal at higher frequency. So yeah, that's one of the advantages, is we can do very high frequency if needed.
Thanks a lot. Fantastic talk. So you have created a fantastic sensor for a fingertip, but you're also considering to go further. So how far are we away from something that can be used to cover a humanoid robot, so the whole body?
Very good question again. The nice thing about these materials is that they don't degrade under hundreds of newtons of load, which is really hard for people to believe until you see it. It's just the nature of them. So we're already looking at feet as well. The problem with feet is calibrating to high load, and then you need a high load calibration setup. So we're building a second calibration stage for high load. That would be the answer.
Maybe another question. So very different, but related to these the theme of those presentations. So your career. Would you do it again in the same way? What would you do differently if you could go back in time with the knowledge that you have now? And can you give an advice to me as someone who has still not done anything in business? Is it still possible for me in my old age to maybe attempt to become a business person?
Yeah, no, another great question. I mean, yeah, it's. I think my trait, we all have our strengths and our weaknesses, and I think it's very important when you are growing a team to recognize yours. I think my primary strength is persistence. I will persist until I solve a problem, hence the multiple fabrication methods and so on. So, but in terms of I would say that any age is fine for a business. So you see the KFC empire was started very late in life. I think the question is always recognizing your strengths and your weaknesses. It's a long journey, but it depends how far, how close you are with the technology, and is it a nascent industry? How much data do you have? This, for me, was a new industry. So that's always probably going to take longer than you think and cost more than you think. So would I go again? If I knew how hard it was to get to this point, probably not. And we're just now finding product market fit. We're about to scale a product from October, which I can't say too much about, but it's going to be our first scalable product, right? And we've gone through multiple generations, four or more generations of iterations with R&D, with big companies, with academia, before we found, a product that we think has universal appeal. So I think it's good to be naive when you start, if you want to be successful.
Thank you.
Any further question? Yes, of course.
Hi, great presentation. I've got two questions. The first one is, do you ever hear now from those 100 investors who didn't invest?
Yeah, not a huge amount.
Right, yeah.
Yeah, if it's of interest, I can tell you a funny story about one of them. So there's a really, I probably can't say his name, but he's the highest net worth person in Scotland, so maybe somebody can look at him. So, he wanted to be the first investor in the company.
Right, yeah.
It's sort of Peter Thiel kind of, let me be the first investor, get a big chunk, but you won't have to work with, multiple investors. It'll just be me, and I'll help you because I've already built businesses and so on. So we had a long meeting, and I told him about the skin and everything. I was very excited. He had already gotten a good reference before. He came with some of his trusted colleagues who manage these investments to visit our offices at the Edinburgh Observatory incubator at the time, the Higgs Center for Innovation, where we were building these sensors at the time. And he was really excited for about half of my presentation, and he was like, go for it. And then I started speaking about avatars. And it just looks really confused, and am I serious? So the presentation ends, they all look really worried. I'm like, what have I done? Because I said avatars for nuclear settings, for space, because XPrize, right? And for healthcare. And he's really worried about these use cases. He's just like, nobody's done that before. That seems pretty risky. So he told me after the after I'd done my presentation, he said, look, if you, we're very interested in this technology, and the skin technology and everything has many applications, outside robotics. So if you cut the avatars out, we'll give you a 5 times higher valuation.
Right, okay, yeah.
And he said, no, but you don't get me wrong, we understand. This just seems very risky. And credit to the guy, he said, you might prove us wrong. He said, we might decide based on this that we don't invest, and you might, 5 years later, prove that, actually you can pull this off, right? I walked away from that deal.
Oh, fantastic. No, that's a great story. No, that's fantastic. And my second question, if it's okay to have a second question, is how are you going to scale up? Are you going to, hand over a design to somebody, or are you going to manufacture the sensors yourself? Have you thought about that kind of, moving into mass markets and things?
Yeah, no, that's a great question. So it's really funny, but yeah, in order to be lean as a startup, again, I didn't know how to build a startup in a non-lean way. I didn't even know how to raise money when I started. So everything from the get-go was designed to be outsourced and super cheap to produce. So we go for, instead of buying screen printers, so I used to work at the Scottish Microelectronics Centre in the clean room, but they didn't have good screen printers. So I worked with a number of screen printing institutes in the UK that have high-end precision screen printers and so on. Anyway, so the answer is, the good thing is it's all manufactured in the UK, and it is all outsourceable. The only thing we have to do is do the final assembly and the calibration in our offices, because the calibration setup is custom and all of that. So, so it's where everything's been designed for manufacture.
Ah, fantastic.
So we're ready to scale. When we're ready to scale this autumn, it means we're very,
Take off, yeah. Ah, fantastic. Thank you very much.
Thank you.